Okay, so I'm going to talk about this particular active particle model. So this work was done with Ayan Santa and Urna Basu. I think both of them are here somewhere. Hi, Urna. These are the details. You can look at the details here, and also there is a poster by Ayan, so you can ask him the details. Since the time is short, so I'm not going to focus on all details, but I'm just I'll bring out some particular features, novel features you see in this kind of models. Okay, so let me start with something I think very basic for this audience. So, like for example, if you take a colloidal particle and look at under the microscope, or let's say 1 micron polystyrene bead. So, and then you look at its displacement over a certain time, let's say 1 microsecond or 1 second. So, what you see is that the typical displacement scales with delta t. So, it's given by this one times some random number, and this random number is Gaussian distributed. So, now if you look at a E. coli, for example, which is more or less similar size to a colloidal particle, so you see that at same time and length scale, they have a very different kind of motion. So they move in a persistent way, so they move there. So this typical displacement goes like ballistically along certain direction, and this direction changes according to some dynamics depending on the kind of bacteria you look at it. Okay, so there can be also thermal noise if you look at in the water, but the magnitude of the thermal noise is usually much smaller than the this kind of motion. So you can most of the time neglect the thermal noise part. Okay, so the minimal model for describing this kind of system, there are many, but these are the most popular models. So this is called this run and tumble particle or active Brownian particle. They essentially describe how does this unit vector changes as a function of time. For example, in the case of run and tumble particle, what it does is that, so you draw a time from some exponential distribution, and this particle moves along that distribution for the time, and then it changes the direction uniformly between 0 and 2 pi, okay, independently at each step. On the other hand, for this active Brownian particle, so this orientation keeps changing continuously, and it undergoes a Brownian motion. Basically, the orientation undergoes a Brownian motion, and this kind of model describe like a microorganism like E. coli, or also some artificial microswimmers like Janus particles. Okay, in fact, you can see this very old paper, like they looked at this bacteria's trajectories. So these are, they call this wild type, basically just pick up from the nature, and you see that it more or less moves in a straight line, and then it changes the direction and it goes like that. So you can also modify those bacteria. Basically, you just screw up their flagella function, and then what it does, it basically has a more or less a directed motion, and it cannot turn immediately. So it basically, to turn it, it has to go through a slightly, so it has basically the direction undergoes a continuous change. So this is like this active Brownian particle, and this one can be thought of like this run and tumble particle. Okay, so irrespective of this model, there are some generic features for this model. For example, if you look at the position distribution in free space, single particle, so you started with a delta function, and you see how it evolves. So usually, so initially there is a peak at the boundary because there is a persistent motion, so it goes away from the place where it started, and then it turns back, and then okay, this distribution changes, and eventually, if you look at the times length scale, which is of the order of the square root of t, so you see this Gaussian distribution as you expect, because at long time, irrespective of the model, because this particle is doing some kind of random motion, and by central limit theorem, it will tell you that it has to be a Gaussian distribution. Okay, so you can also look it under confinement. So if a simple Brownian particle, like the first slide I showed, so if you put this in a confinement, so what you see is that it goes to a steady state given by this Gibbs distribution. And so, for example, if you have a confining potential, something like that, what you will see is that it is a peak at the center. But for the active particle now, there are generically two phases. In one case, it is called the passive phase because this trap gives you a relaxation time, and if your persistent time is much shorter than this relaxation time, so then you see something similar to this state. So this is like a passive steady state. On the other hand, if your relaxation time is much larger than the persistent time is much larger than the relaxation time, this particle keeps going until it cannot move. So what you see is that you see accumulation at the boundary. So therefore, for a given active particle, so if you tune the strength of the trap, so you will see this shape transition going from a passive-like steady state to an active-like steady state. Okay. So these are the system where you have one time scale, one persistent time scale. But now, so what we looked at a model which has a two time scale. So there are systems actually what you see, like for example, this model, these are called microscopic centers. So they move more or less like an active Brownian particle, but they suddenly reverse their direction completely. So it just, they reverse it 180 degree. So you see some kind of motion like this. So there is also like this, so it almost going like this active Brownian particle, and suddenly it reverses this direction. Okay. And these models, they are also artificial particle where you basically coat this particle with this titanium dioxide this thing, and then depending on what kind of light you are shining, it basically moves one way or the other. Okay. So if you want to model this particle, the minimal model is basically like this active Brownian particle, but then there is another variable sigma which takes +1 or -1. Okay. So sigma independently, irrespective of theta, it changes between +1 and -1. Okay. So you just see something like that. So now, if you look this particle, so there are these two time scale. One is this gamma at which this 1 by gamma at which this direction changes, and the other one is this diffusion time scale. So you look at, initially you have this directed motion, and eventually it goes to this Gaussian isotropic state. But this case, if you look at it, it goes through an interesting intermediate state. Okay. And what we want to focus on this intermediate. So you see that this one, it has a asymmetry, it stays for a long time, and we are going to basically focus on this state. Okay. So in this state, so we are going to focus on only one variable in this talk. So there is a asymmetric state, and if you look at the fluctuation along the perpendicular direction of the initial orientation, so you can write down this equation for that, effective equation for that. Okay. So this is like a Brownian motion with a diffusion coefficient which itself is a Brownian motion.
4 minutes,
okay. Yeah. So and then you actually solve this, and what you see is that you have a very interesting scaling distribution. So the first of all, the transverse direction, the perpendicular direction moves ballistically, and you have a scaling form which you can actually compute exactly, which is this product of these two gamma functions. You can also look at the stationary state. So as in the earlier case, you have these usual two stationary states, but on top of that you have now this other stationary states, and it's precisely coming from the because of this interplay between these two time scales. So where either in the passive state or in the active state, there is a diverging peak at the center. Okay, and one can in fact characterize this diverging peak, and it's a logarithmic diverging peak. So I'll not go into details. So what you see is that in the stationary state, in the passive scale, the tail is like a Maxwell distribution, and in the active state, it's diverging. But on both cases, there is a diverging peak. Okay, so you can in fact find out more detail, and you see that you can show that so it has this given by this scaling function is given by this, and this scaling function has a Boltzmann-like tail, but it has a logarithmic divergence at the center, basically. Okay. So the take-home message is basically that active particles having multiple time scales can exhibit interesting novel features due to the interplay between those time scales.